Okay, so this is an exponential equation because we see that the variable is in the exponent. And the way we know how to solve these exponential equations is by trying to get both sides in terms of the same base. Now, the base being used here is obviously 5. This says 5 to the 3 minus 2x. So we're going to try to get this other side, this number on the right side, in base 5 as well. Which means, let's see if we can get 25 written in terms of 5, and of course we can. 25 is really 5 squared. We want to make sure we're writing them both in terms of the same base. So this turns out to be that my equation is actually 5 to the 3 minus 2x equals 5 to the 2. Now, once you have the same base, then obviously it means the exponents have to be equal as well. So we can ignore now these base 5s and just put the 3 minus 2x, which is the exponent over here, equal to the 2, which is the exponent on this side, and just solve this equation. So I'm going to bring the 3 to the other side, which will give me negative 2x equals 3 minus 2, which is negative 1. And then, of course, I'll divide both sides by negative 2. This is just a regular equation. So negative 1 divided by negative 2 is just 1/2. And my answer for this equation is 1/2. Those are the answers I did get from some of the students, and that is absolutely correct. All right, so now let's look at the second equation. The second equation is an equation that has logs in it. And it says simplify the log base 49 of 7. And actually is not an equation, it's just an expression. But remember what we said we're going to do when we have a log expression. I'm going to put it right over here so we'll keep it in mind. If we have the log base b of a equaling c, that translates to the base b, the subscript, to the exponent, which is the number on the other side, the c, equal to a. These two things are equivalent. They say exactly the same thing. They're coming at it from a different angle. It's like saying 2 plus 3 is 5, and then you could say 5 minus 3 is 2. It's basically the same facts. That's the same thing with these logs. So if I want to rewrite anything, it looks confusing in log format. So sometimes what we do, or most times what we do, is we convert from the log form, we go back to what's called the exponential form. And in order to do this, I'm going to just call this thing x, or I could call it anything I want. I just need what is it equal to so that I can convert this to exponential form. So my base is going to be the 49. The 49 is the number that's going to get the exponent. The exponent is the number that we don't know. That's what we're looking for. That's this thing on the other side. So it's 49 to the x power equals, that's always equal to the number that's right next to the word log. Remember, this is a subscript. It's below the line. The number that's next to the word log is 7. So in exponential form, this becomes the equation 49 to the x equals 7. Now, again, we're talking about exponents. Now, we know the relationship between 49 and 7. I have to do the square root of 49 in order to get 7. So how do we express the square root as an exponent? So remember, we said in this chapter, we're never going to use that radical sign. We're going to go to exponent, and the 1/2 exponent means the same thing as the square root. So it must mean that this x is meaning the square root in exponential form is 1/2. So again, once we've switched it from the logarithmic form to the exponential form, it becomes easier to figure it out. And it turned out these are two different examples, but they both had the same exact answer of 1/2. Okay, so now I want to continue from here. I'm going to leave this on the board because it's going to be important for us to. Let me also leave on the board the 3 basic properties of logs. The log, I'm not gonna, this applies to any base. I'm not putting in the base. Remember, when you don't put in the base, it's understood to be base 10. The log of x times y equals the log of x plus the log of y. This was the last thing we were talking about on Tuesday. That when we're multiplying numbers, what we do to their logs is we add them. That's because if we keep in mind, the logs are exponents, and the rules of logs are really the rules of exponents. And we know when we multiply numbers, what we do to the exponents is we add them. Similarly, the second rule is if we have the log of x divided by y, when we divide numbers, what we do to their exponents is we subtract them. So the rule in terms of logs is the log of x divided by y is the log of x minus the log of y. Be careful that you always put the positive one as the numerator, the negative one, the one with a minus in front of it, means it's in the denominator because it has to be a divisor. Anything that's in the denominator ends up having a negative in front of it. That was rule 2. Rule 3 had to do with exponents. If I have something like the log of x to some exponent n, then because with exponents, when you have one exponent and then you put another exponent on top of it, what you're doing is multiplying the exponents. This becomes the n, the one exponent is multiplied by the log of x, which is the other exponent. Remember, the log means the exponent. So here, the exponent becomes the coefficient. And remember, this rule also takes care of the radicals because any radical can be written as an exponent. And these are what they are called. So these are your basic rules that have to do with logs, switching from log form to exponential form, and the 3 properties of logs, or the rules of logarithmic, as I call them. So how does this work? So as I said, what I want to do is I want to do the last couple of topics, and then we'll start doing a complete review of the course. So one type of question that we can have is something like this. I have a question like this. We're talking about equation. Basically, what we're going to be talking about today are log equations and exponential equations. So let's say I give you something like this. The log of 3x equals 2. This is a log equation. Most log equations are solved by switching from the log format to the exponential format, because then it looks easier to understand. Remember what I told you, that if no base is written by the log, it's not a mistake. It means when I just write log, it really means log where the base is 10. So if I see this equation, the log of 3x equals 2, I know there's this 10 understood to be here. And if I switch this from the log format to the exponential format, my base is going to be the 10, because that's the subscript. The number on the other side of the equation is the exponent. And that equals what's right next to the log. I'll keep repeating this because it's a translation problem. Once you understand it, once you can translate, then you'll be able to solve. Of course, now this looks easier to deal with. First of all, 10 squared we know is 100. So this is giving me 100 equals 3x. And then I divide everything by 3. And my answer is, as a fraction, 100 over 3. And you can leave it in fractionals form. You could change it to decimal, but usually, especially in a multiple choice test, they probably would leave this as the answer. So this log equation can be solved by switching it to exponential form. Look at this equation. I'm going to do another log equation. Here is also an equation that has logs in it, called a logarithmic equation. It's telling us that the log base 2 of x plus the log base 2 of 3 equals 1. Now, if I follow my rules that I've been giving you, I see the base here is 2, it's not base 10, but I should switch this from the log form to the exponential form. But the problem arising here is that there are 2 logs over here. The rule of switching from log format to exponential format depends on you having the word log on one side and a number on the other side. You can't have 2 logs. If you have 2 numbers, you'd have to combine them. But here we have 2 logs. So we want to combine these 2 logs into a single log as well. But remember, working with logs is not the same as working with numbers. I can't just add these 2. So I go back to this rule. I know that when I have 2 numbers being multiplied, if I have x times y, then what I do to their logs is I add them. In other words, if I'm going backwards, if I'm adding 2 logs, if I have log x plus log y, if I add those 2 logs, that really means what I'm doing is I'm multiplying the numbers. So when I have 2 logs being added and I want to contract it to a single log, I've got to take the 2 numbers and multiply them. This is x times 3, which I'm going to call 3x. So this is the big thing to remember. If you have a log equation and it's a single log equaling a number, right away go to the exponential form. If you have a log equation that has more than 1 log on the side, then you're going to have to contract. You're going to have to put them back into a single log. And you're going to have to use one of these 2 rules. If the sign in between them is plus, it means that you're multiplying the numbers. If this would have been a minus, it would have meant that I would have been dividing. And remember, the positive one it would go on top and the negative one would go on the bottom. But this is plus, so we're multiplying. Now, of course, I can solve this equation because I can now go to the exponential form because I have one log equaling a number. So this becomes 2. The exponent is a number on the other side, which in this case is 1, equals 3x. Well, 2 to the 1 is just 2, so this means 2 equals 3x. And therefore, my answer for x is 2/3. Let's try another example. I'm going to do one more with you, and then I'm going to give you a couple to try on your own. So I have this equation, the log base 3 of x plus 2 minus the log base 3 of x equals 1. Again, this is a log equation because I have something that says logs equaling a number, except again, I have the same problem. I can't go directly to the exponential form because there are 2 logs over here. So I have to contract this, condense this back to a single log. And I see the sign in between the 2 logs is minus. I'm subtracting the logs. And I know when I subtract exponents, which logs are, that means I'm really dividing the numbers. So this in contracted form would be log base 3 of the x plus 2 over the x. Remember, the one with the negative goes on the bottom, the one with the positive sign in front, or no sign, which means it's positive, goes on top, and that equals 1. We have contracted this log equation into a single log. Again, when there's adding, we multiply the 2 numbers. When we're subtracting, we divide. In other words, we divide what is the 2 numbers or the 2 expressions that are after the word log. And again, now we have a single log equaling a number, so we can go to the exponential form. My base here is 3. My exponent is the number on the other side of the equal sign, which is 1. And that equals the x plus 2 over the x. Now, since this side is a fraction, I'm going to write this side as a fraction also by putting it over 1. So what I really have is 3 to the 1, which is 3 over 1 equals x plus 2 over x. I'm just going to go over here because I don't want to erase this yet. And this is just a regular, what we call a proportion. We cross multiply. 3 times x is 3x. We've learned how to do these kind of equations. Equals 1 times x plus 2, which is x plus 2. We can solve these fractional equations because it's a single, called the proportion, one fraction equaling another, so we cross multiply. And again, I'll subtract x from both sides. This is now an easy equation to solve. I get 2x equals 2. And that gives me my answer is x equals 1. I want to make one comment. it is possible that you could get an extraneous root. Remember, we had cases during the term where we had extraneous roots. We had case where we had a fraction, and if the answer made the fraction negative, the fraction denominator turned out to be 0 with the answer, we couldn't use that answer. We called it an extraneous root. We had it when we had a square root. We couldn't, if the answer made the fact that a square root is negative, we couldn't use it. We had to throw it out. We could have an extraneous root in log equations as well, because the answer always has to make what we're taking the log of a positive number. You can never take the log of a negative number or of 0. So if your answer, when you put it back, makes it a negative number, then you can't use it. But notice, my answer was 1. And when I put the 1 back into the x, and the first one I got 1 plus 2, which is 3, that's positive, no problem. And this is 1 is also positive, it's not a problem. Again, we have to be sure that we're only using answers that make my logs positive. We have to be careful with this when we had radicals and when we had absolute value equations, and we have to be careful with it now as well. Okay, I'm going to erase this, and I'm going to do one more problem with you before I give you problems, a couple of problems to try on your own. So suppose we have this log base 3 of x plus log base 3 of x minus 2 equals 1. Okay, again, we want to solve this log equation. We want to figure out what x is equal to. So again, we are faced with the same problem. We have more than one log on a side. So we have to first get these two into a single log. Okay? I look at what's in between the two logs, and I see the sign is plus. That means that originally, if I'm adding the logs, it must have been that I was multiplying the numbers. So I'm going to contract this to the log base 3 of x times x minus 2. The plus, when we add logs, it means we're multiplying the numbers. And of course, this I could really expand or remove the parentheses. This really means the log base 3 of x squared minus 2x. Just using the distributive property on the x times the x minus 2. And of course, now that I have a single log equaling a number, I can change it from the log format to the exponential format. Again, my base here is 3, so I'm going to do 3. My exponent, the number on the other side, is 1. that equals x squared minus 2x. And of course, this 3 to the 1 is just 3. So what I have is 3 equals x squared minus 2x. Now this equation happens to be a more complicated equation because I see what I have to solve now. It's just a regular algebra equation. Notice we went from the log form to the regular things that we had learned previous. This is a quadratic equation that has to be solved. So I have to get it equal to 0. I'm going to bring this 3 to the other side. I'm just going to write it this first. So this gives me x squared minus 2x minus 3 equals 0. I just switched it around. And I'm going to have to use my AC method. My AC is -3, and my B is -2. Remember how we factor? So we're looking for two numbers that are going to multiply to -3, which means one's going to be positive and one's going to be negative. And when I combine them, I'm going to get -2. Well, obviously, the numbers are multiplied to 3 are 1 and 3, and it's going to have to be a +1 and a -3, so that when I combine them, I will get -2. So this becomes x squared minus 3x plus 1x minus 3. And when I factor it, let's go over here. I'm factoring now using grouping. On my first group, my common factor is x, so that becomes x times x minus 3. In my second group, there's no common factor, so I have to use 1. So there's a +1 times x minus 3, which then gives me x minus 3 times x plus 1 as the factoring of this quadratic equation. And now I set each of these equal to 0. X minus 3 equals 0. And when I solve that, I get x equal to 3. And x plus 1 equals 0, which gives me x equals to -1. So when I solve this, I actually got two answers. But let's check if both answers are good. Remember, I can only use an answer if it gives me if the number next to the word log is positive. So when x is 3, this is okay. So the log base 3 of 3, this is positive. And when this is 3, this is 3 minus 2, which gives me 1, which is also positive. So 3 is a good answer. But look what happens when we try to use -1. But I erase this and replace this with -1. If my x is -1, I right away see that I'm trying to do the log of a negative number. That is no good. It's an extraneous root. We cannot use it. So my only answer to this question is x equals 3. I cannot use the other answer. And if you had a multiple choice question and it gave you both answers and you picked 3 and -1, your answer, even though you did all the work correct, your answer would be incorrect. Only the 3 is correct. The -1 is an extraneous root because by definition, you can only do the log of a positive number. It can't be 0, it can't be negative. Okay, so I think you're now ready to try an example on your own. Erase this and put. log base 4 of x plus log base 4 of x plus 6 is equal to 2. Okay, see if you can solve that equation, that logarithmic equation. While you're doing that, I'm going to take attendance. Jesus Antonio. Jackson Avila. Good morning. Tiffany.
I'm here.
Hi, Tiffany.
Hi.
Caleb Brantley. Tashana Caesar. Hi, Tashana. Dion Carter. Wensley. Tatiana. Awa. Hi, good morning. Ashay Douglas. Eliana Estate. Emily Gomez. Anastasia. Zanabu. Ismail. Jaden. Not doing too well today. Ashiana. Hi, good morning. Anijah. Thomas.
I'm here.
Hi, good morning.
Morning.
Paul.
Good morning. Here.
Good morning. Ashley. Angelica. I know you're here, Angelica. Tayon. Hi, good morning. Akeem. Akeem Richards. Craig. Giovanni. Devonley. Najee. Okay, 1, 2. I'm still giving you a few minutes to try to work on this. Okay. Shoshana has an answer. And Awa has an answer. Good. So just giving you the rest of you a couple more minutes. Okay, I see. A few people have come up with the same answer. Let's see if that's the right answer. Okay, so again, we have this situation where we have two logs on one side equaling a number. And we said what we want to do is make sure we have only a single log in the question before we try to switch it to the exponential form. And again, I see a plus between these two logs. So that means that I'm going to change this to log base 4 of x times x plus 6. And of course, this x times x plus 6 can be expanded, or we can use the distributive property. It's x squared plus 6x. And now what we have to do is, now that we have just one log on this side and a number on this side, we're going to switch this to exponential form. My base here is 4. So this is 4. The number on the other side is the exponent. So that means 4 squared equals x squared plus 6x. And the 4 squared, that's where you have to be very careful. Don't let it set it equal to 2. It's equal to 4 to the 2 exponent. 4 squared is 16. So this becomes 16 equals x squared plus 6x. And again, this is a quadratic equation. I'm going to bring the 16 to the other side. So I'll get 0 equals x squared plus 6x minus 16. And again, we're going to use our AC method, where our AC is negative 16 and our B is 6. So we're looking for two numbers that when we multiply them are going to give me negative 16, which means, of course, one's going to be positive and one's going to be negative. And when we combine them, we're going to get a positive 6. Well, I think you realize that that's going to be 8 and negative 2, because 8 times negative 2 is negative 16, and positive 8 combined with negative 2 gives us positive 6. So here we have x squared plus 8x minus 2x minus 16. And taking our first group, we have a common factor of x. So this becomes x times x plus 8. And the second group, I have a common factor of negative 2. So that becomes negative 2 times x plus 8. So we get x plus 8 in one parenthesis, and in the other parentheses we get the x minus 2, and that gives me x plus 8 equals 0, gives me x equal negative 8, and x minus 2 equals 0, gives me x equals 2. Again, I can't assume both answers are correct, so I check. Notice when I use negative 8, I don't have to go further than here. I have to always go back to that original equation. And when x is -8, I'm taking the log of a negative number, no good. It doesn't matter what happens in the second. As soon as this is negative, out it goes. What about when x is 2? So this is good. When x is 2, this is a positive number. And then I go to the other one, this is 2 plus 6, which is 8, which is also a positive number. So x equals 2 is the only answer. Do not give the -8 as an answer, and that's the answer that I saw a few people did give. What else would we do? Okay, so I want to go now. I think we're pretty good about solving logarithmic equations. Again, the basic rule is get it to a single log. If it already is a single log, if there's only log once, that's fine. If not, if you have 2 logs added, then just multiply the 2 expressions. If you have 2 logs subtracted, then you divide the 2 expressions to get a single log. And once you have a single log, then you can go from the log format to the exponential format. Now I want to go and show you how we can solve exponential equations using logs. But before I do that, I want to explain to you what you're going to see on your calculator. Now, I can't exactly tell you where your log buttons are on your calculator, but usually on a scientific calculator, you'll see one button that says log. And then right near it, either above or below it or next to it, you'll see another button that says ln. These both are buttons that have to do with logarithms, but they're very specific. The regular log button deals with logs where the base is 10. We've mentioned that it's called a common logarithm. And when we write the word log without any base there, it's understood that the base is 10. If it's any other base, we have to put in the base. So what is this ln button? So there is a special number called e. E is called the natural number. It's a very important number that comes up in a lot of different equations and a lot of different situations. And it has to, when you're working with compound interest or populations, there are formulas that are used that use a special number e. It's equal to 2.718, I think another, maybe 2818, I don't know what it is exactly. I know it starts 2.718. It happens to be, I don't know why they call it a natural number, because to me it looks very unnatural. It's non-ending, it's non-repeating. It's sort of like the number pi, or like we have the square root of 2. It's not, it's what we call an irrational number. Because it's such a complicated number, instead of calling it that whole number, we just use the symbol e to represent it. this ln is the log where the base is e. So ln is just another type of logarithm. Remember, every type of logarithm you're going to deal with is going to have a base. It could be the base is 2, it could be the base is 12. The base has to be a positive number, but it could be any positive number. If it's 10, then it's what we call this common log, and it's right here on our calculator. If the base is e, then it's also right on our calculator. And if I want to do anything, like if I want to find out what is the log base e of 17, I wanted to do that, all I have to do is go to my ln button on my calculator. I can't do this any other way but on my calculator, and press my ln button, and then just put in the 17. And I get something like 2.833, keeps going on. Usually the answers are these long decimals, but again, it's not anything you can figure out on your own, but your calculator is calibrated. So if I ask you what is log of 17, which of course means your base is 10, then you press your log button and you get 1.230. Notice, of course, you're getting different answers because the bases are different, but these are two different buttons that are used on your calculator. This ln button, actually, this whole E business is very important when it comes to calculus. So that's why it's going to be on your calculator. For our purposes, we really hardly ever use it. Okay. Now, just having mentioned how the calculator works, we're going to be using our calculator. Suppose I wanted to solve an exponential equation that looks like this. 5 to the x equals 20. Now, we've solved exponential equations previously, but when we solved them, it was possible to put both sides of the equation in terms of the same base. Obviously, since this says 5 to the x, the base being used here is base 5. But when I go to the 20 and I try to put 20 in base 5, it doesn't work because 5 to the 1 is 5, but 5 squared, 5 times 5, is already 25. We went right past the 20. So it's not possible. And in most cases, that's what happens in exponential equations. It's not possible to get both sides in terms of the same base. But there is something that can be done using logs. What we're going to do is we're going to take the log of both sides. When I say take the log, I'm going to put the word log in front of it. The log of 5 to the x will equal the log of 20. In other words, obviously, if the two numbers are the same, then if I put them into my log and press my log button, I get the same exact answer. Now, notice I wrote log without any base in here, meaning I'm using a common log. I'm using log base 10. And the reason I want to use log base 10 is because I want to eventually use my calculator. So I could have used ln because that's on my calculator, or I could use common logs. I usually use common logs. Now, what is the advantage of using the log button? This example over here, this rule over here will tell us why. When we're dealing with logs, if we have an exponent, if we have log x to the n, then that exponent becomes a coefficient, becomes a multiplier. So now that I have these in terms of logs, I can take this exponent x and put it out here in front of the word log. So this will read x log 5 equals log 20. I've gotten the exponent to be a coefficient. That can only happen because I have logs. Now, I'm trying to solve for x. Over here, when it's in the exponent, it's really hard to do. But over here, the x is just a multiplier. And I know if I want to get x, all I have to do is divide by log 5. This is x times log 5. To get the x alone, divide by log 5. But of course, if you're dividing by log 5 on one side, you've got to do it on the other side as well. And now I go to my calculator and I press log 20 and I close my parentheses and then I divide because I want to do a fraction and I press log 5 and I get the answer. Usually it comes out to a very long decimal. Let's go to the nearest hundredth. Then the answer would be 1.86. So it becomes a relatively easy question to answer. Of course, it can only be done if you have a scientific calculator. I've been telling you from the beginning of the term, we're now at the end of the term, you need a scientific calculator. Yes, you must have a scientific calculator with sines and cosines in it, with logs on it. Notice I'm going to show you that this really works. Remember what I came up with. I came up with x equaling 1.86. So if I go back to my original equation to check, I must get 5 to the 1.86 exponent equaling to 20. Now it's not going to come out exact because I rounded off this answer. But on my calculator, I'm going to go 5, then I'm going to press my exponent button, and I'm going to put in 1.86, and I get, when I do that, I get 19.956. It's a little off because I rounded this. If I wouldn't have rounded it, it would come out exactly. But we see that this is the correct answer. So we're able to solve exponential equations even when the exponent, even when the number on the other side can't be written in terms of the same base. Let me give you another question. Let me give you one to try. Okay, I'm going to give you this one to try. 3 to the x equals 5. I want the answer to the nearest tenth, nearest tenth. And I'm gonna give you a couple minutes to try it on your own. Okay, we have a couple of people who came up with the answer, though, so let's see if we're gonna come up with the same answer. Again, we have this 3 to the x equals 5. The first thing is to try and put them in the same base. Well, obviously, the base being used here is 3, but 3 to the 1 is 3, and 3 to the 2 is already 9. So obviously, there's no way we're going to get 5 written as 3 to some exponent. So I have to use my log method. I'll put the word log in front of both of them. Log 3 to the x equals log 5. And then I can take the exponent and make it a coefficient. X log 3 equals log 5. And then to get the x alone, I'm going to divide out the log 3, because these two are being, since they're right next to each other, they're being multiplied. To get rid of it, I have to divide. So that's what I have to do on my calculator. I have to put in log 5 and then divide that by log 3. And I get comes out to be 1.46497, et cetera, et cetera. I said I wanted it to the nearest tenth, which means I have to stop after the first place after the decimal. The next number is a 6, so I make this 1.5, which is the answer I've gotten. A bunch of people came up with that answer, and that is completely correct. Excellent. So we've learned how to solve basic logarithmic equations and basic exponential equations. Even if we can't get them in terms of the same base, we can do it using the logs. Just want to go back to the last thing that we had been talking about, and that's using these rules to expand logarithmic expressions. Okay, so let's say I have this example. I'm going to do this and then you're going to do one. Suppose I have log base 5 of 4x to the 5th divided by 9a squared. And we want to expand it in terms of these log rules. So today we were going the opposite. We were taking the expanded version and contracting it. Now I want to take a contracted version and expand it. And remind you, we're going to use these basic rules. When we're multiplying numbers, we're going to add their logs. When we're dividing numbers, we're going to subtract their logs. And when we have an exponent, it's going to become a coefficient. So the first thing I deal with is just the multiplications and divisions. And then afterwards, I'll go back and deal with the exponents. So the first thing I see is in the numerator, I have anything in the numerator is going to become positive. Anything that's in the denominator is going to become negative, because anything that's in the denominator is going to be used as is being divided by. So the first thing I see in the numerator is I have a 4 times an x to the 5th. So therefore, in terms of the logs, it's going to be the log base 5 of the 4 plus, remember when we're multiplying, we add their logs, log base 5 of x to the 5th. I just have to keep writing this base here. And now I'm going to be subtracting the log. Let me start this a little lower. I'll end up hitting that. Log base 4, log base 5 of x to the 5th, minus, now we're doing log base 5 of the 9, and also we're subtracting the log base 5 of the a squared. Don't put a plus in between them. Even though these two things are being multiplied together, they're both in the denominator. They're both really, when we put these minus, we're talking about the whole, not what's happening between these two things, but what is it doing in its, what is its function in the whole expression. And the 4 and the x5 are in the numerator, so they are the positive ones. But the 9 and the a squared are both in the denominator, so they're both really being used as divisors. Now I go back and I look for exponents. And I see an exponent here and an exponent of here. So I leave this log base 5 of 4. This exponent becomes plus 5 log base 5 of x, because the exponent becomes the coefficient. This stays log base 5 of 9. And this 2 becomes minus 2 log base 5 of a. And that's the expanded version. This is the contracted version, the single log version. This is the individual logs. This is what we're doing to each of the logs. We're adding these 2 logs because we're multiplying the numbers, and we're subtracting them, these 2 logs, because we're dividing by both the 9 and the a squared. Okay, let me give you one to try. Suppose I have log, and I'm not putting any base in, so you know it means base 10 of the 4th root of a divided by b to the 2nd c to the 3rd. Let's see if you could write this in an expanded version. Okay, let's work on this together. Let me remind you that when we're dealing in this chapter on exponentials and logs, we don't like to deal with radicals. So anytime I see a radical, I change that from radical form to exponential form. Remember, the 4th root of a is the same as a to the 1/4 power. You can write the radical as 1 over the index, and that gives you the exponent. The 1/2 exponent let's remember the plane, the square root is the 1/2 exponent. That's most common, but any index, remember here the index is understood to be 2. Here the index is written as 4, means a to the 1/4. So actually what I'm asking you to do is the log of a to the 1/4 power over b squared c to the 3rd. And we're going to do the same thing. First of all, there's no base written in. It means it's a common log. It means we're dealing logs. Base 10, but it doesn't matter. Whatever base is written in, that's what we just carry it through. So this is going to be dealing first with the multiplications and divisions. We're going to have log of a to the 1/4, because that's on the top, it's positive, minus the log of b squared, and also minus the log of c to the 3rd. This is also a minus because it's also in the denominator. And now I'm just going to go back and take all the exponents and make them into coefficients. So this is going to become 1/4 log a minus 2 log b minus 3 log c. And that's how we would write this expression in its expanded version of individual logs. Excellent, Awa. Okay, I'm going to leave you here. I'm going to look out for some homework on delta math. But don't forget, if you haven't completed the test on delta math, test number 3 on delta math, you can still do it. You probably will get only 90% of the credit. So if you get a 90, you'll get an 81 instead of a 90. But if you want to let me know, I will extend the time that you're allowed to do that test. Also, until a week from Monday, not this Monday, but a week from Monday, there is a test on Blackboard it's a pre-test for the final exam. It is also to be done for a mark. It has to be completed. You have 2 times. You can try it twice, and I will accept the better mark as your mark. Have a nice weekend, and I'll see you on Tuesday. Oh, and Dami Lola is telling us that today there is tutoring starting at 12 o'clock. So right after this class, you have time to have a break, and then you can go to tutoring. Okay, have a nice weekend, everybody.
You too.